Good day everyone. In this video, I'm going to discuss about the 4 cover topics in the finals. So it includes indeterminate forms, L hospital rules, Cauchy, improper integrals, and other improper integrals. So first, before moving to the two examples that I'm going to share, which is about the indeterminate form, I'm going to first discuss what is indeterminate. So indeterminate is when limit of x as it approaches to a, let's say we have f of x and over g of x, and if it results into 0 to 0, it means it is indeterminate, same as if it results to infinity over infinity. That is when we call it indeterminate. Now let's move to our first example, which is limit of x as it approaches to 0, sine x over x. So first that we need to do is we need to apply the limit to know if it is an indeterminate or it already has its limit. So first is we need to apply the limit, which is 0, to our function. We have sine 0 over 0. So since sine 0 is equal to 0 and the denominator is equal to 0, we have a result of 0 over 0, which is an indeterminate. So in this case, since our function is indeterminate, we can apply the L'Hopital's rule to find the limit of this function. So in L'Hopital's rule, we are going to use the first derivative. So we will find the first derivative of our function. So we will find the derivative of sine x and the derivative of our x separately. So the derivative of sine x is equals to cosine x, and the derivative of x is equals to 1. So we will write it as limit of x as it approaches to 0 cosine x over 1, applying the first derivative. So since cosine 0, we need to apply again the limit. So we have now cosine 0 over 1. Since cosine 0 is equals to 1, we have 1 over 1, which is equal to 1. So our limit of this function, sine x over x, is 1. Now for our second example, we have here limit of x as it approaches to infinity, x cubed e raised to negative x raised to squared. So we have here limit of x as it approaches to infinity. Since our exponent is negative, we can rewrite it as x cubed over e x to squared. So now we have to apply the limit, which is infinity. So we have infinity cubed to the e raised to infinity raised to squared is equals to infinity over infinity. Since it is indeterminate, we can apply the L'Hopital's rule to find its limit. So for our first derivative, we have here limit of x as it approaches to infinity, 3x squared over 2x e to the x raised to squared. So we have here limit of x as it approaches to infinity, 3x over 2e raised to x raised to squared. So is equals to, apply again the limit, which is the infinity. We have 3 to the infinity, 2e raised to infinity squared is equals to a infinity over infinity. Since the result is indeterminate again, we will apply another derivative. So next, we have limit of x as it approaches to infinity. So now we will base it to the first derivative function natin. So now we will base the derivative for the another derivative, since the result is infinity over infinity, which is indeterminate, to the 3x squared kanina. So we have now 3 over 4x e to x squared over. Now we will apply the limit. So now we apply the limit and it results to 0. Therefore, limit of x is the approaches to infinity, x cubed e raised to x squared is equals to 0. Now for our third example, it is about improper integral with infinite limits of integration. So for our third example, we have here integral of x over 1 plus x squared dx, where the upper boundary is infinity from negative infinity to infinity. So let's have integral of x over 1 plus x squared dx negative infinity to infinity is equals to, apply the definition based on the book of Stewart. So we have limit of t approaches to negative infinity to the left. Integral of x is over 1 plus x squared dx t to 0 plus limit of t to the infinity to the right, x integral of x over 1 plus x squared dx, where it bounded to 0 to t. So next is we will have the integral of the functions. So we have limit of t approaches to negative infinity, which is the left. We have 1/2 ln 1 plus x squared, and then remain the boundary t to the 0, plus limit of t approaches to infinity to the right. We have 1/2 ln 1 plus x squared, and then our boundary 0 to t. So we have here now limit of t approaches to negative infinity, 1/2 ln 1 plus 0 squared minus 1/2 ln 1 plus t squared. So we apply our boundary. And then another for the next is limit t approaches to infinity, 1/2 ln 1 plus t squared minus 1/2 ln 1 plus 0 squared. So now let's evaluate it. Limit of t approaches to negative infinity, 1/2 ln is 1 from the 1 plus 0 squared, it is 1, minus 1/2 ln 1 plus t squared, plus for the another function we have limit of t approaches to infinity, 1/2 ln 1 plus t squared minus 1/2 ln 1. So now let's evaluate it further. Limit of t approaches to negative infinity, it's equals to 0. So 1/2 ln 1 is 0. So minus 1/2 ln 1 plus t squared plus ln t approaches to infinity, 1/2 ln 1 plus t squared minus 0. So to simplify, we have 0, and then this one for applying the limit we have infinity plus infinity minus 0, so it results to negative infinity plus infinity. Therefore, the function integral of x over 1 plus x squared from negative infinity to infinity is divergent. Now for our last example, we have here integral of dx over x minus 1 raised to 2 with the boundary of 0 to 2. So first we let c is equals to 0. So integral of dx over x minus 1 raised to 2 with a boundary of 0 to 2, we apply definition according to the book of Stewart. So it is equals to limit of t approaches to 0 to the left, and integral of f of x dx 0 to t plus limit of s approaches to 0 to the right, integral of f of x dx approaches to the boundary approaches to s to 2. So now let's apply that definition. So we have limit of t approaches to 0 to the left, integral of dx over x minus 1 squared from 0 to t plus limit of s approaches to 0 to the right, dx minus x minus 1 squared from s2. So we let u in this case. So we have u x minus 1 du dx. So applying it of substituting, du over u squared, integral of u negative 2 du as we rewrite it, and then applying the integral, we have u negative 1, since u negative 2 plus 1 is negative 1 over negative 1 based on the integral. So we can rewrite it also as negative 1 over u. Now we rewrite it to our function. Limit of t approaches to 0 to the left is equals to negative 1 over u as it approaches to 0 to t plus limit of s approaches to 0 to the right, negative 1 over u s to 2. Now we write back the value of our u. So we have limit of t approaches to 0 to the left, negative 1 over x minus 1, 0 to t plus limit of s minus s approaches to 0 to the right, negative 1 over x minus 1 s to 2. Next is limit of t approaches to 0 to the left, negative 1 over t minus 1 minus negative 1 over 0 minus 1. So we apply the boundary, plus limit of s approaches to 0 to the right. So we have negative 1 over 2 minus 1 minus negative 1 over s minus 1. So now we evaluate it for limit of t approaches to 0 to the left. We have here negative 1 over t minus 1 minus 1 plus limit of s approaches to 0 positive, which is to the right. So we have negative 1 plus 1 over s minus 1. So we apply the operation. So we have negative 1 over 1 minus 1 plus negative 1 plus 1 over 1. So it does not exist. Therefore, the function is divergent. And that's all. Thank you.